In this video, I'm going to cover some of the background information that is necessary for you to learn how to handle an inverse trig function. The inverse trig functions are covered in section 4.7 in your textbook. What you're going to take notes on is basic vocabulary, definitions, information about the graphs, and so forth, all of which applies to functions in general, and all of which is necessary to understand how and why the inverse trig function works the way that it does. I want to start with the definition of a relation, because a relation is the most general type of pairing of inputs and outputs. There are no restrictions on a relation. It doesn't matter whether the input is used twice and output is not used at all. Very nonspecific. So we have any pairing of inputs to outputs. No restrictions. Here is an example of a relation. We could take a set of inputs, and in this set we could put the numbers 2, 3, and 4, and we compare them with a set of outputs. We'll put 7, 8, and 9 in this set. So this is our set of inputs, and this is our set of output values. And it doesn't matter how I match them up. This is a relation. This type of representation of a relation, where we have the inputs and the outputs in two sets like this with the arrows going in between, is called a map. And you recall from algebra and our discussion of the graphs of sine and cosine that the input values we're going to call the domain, and the output values we're going to call the range. And your domain values are typically x values, and your range values are typically y. One other way to represent this relation, instead of the two circles here that I have with arrows going in between, could be a set of ordered pairs. So over here I'm going to draw the same relation, but it's just going to be represented by ordered pairs instead of the circles. So we have an input of 2 mapping to an output of 8. So we create the ordered pair 2, 8. And again, here you can clearly see the relationship between x and y. Continuing down, we'd have the ordered pair 3, 7, 4, 8, and 4, 9. A different way to represent the same relation. We use ordered pairs a lot in this class to try and explain what is going on behind the scenes with any type of function, because you can clearly see the inputs and the outputs and how they go together. Once we move away from a relation, we have a function. And a function is a relation, but it has some restrictions. So it's a relation where each input is used exactly once, or each input is paired with exactly one output. So we have a relation where each input is paired with exactly 1 output. A different way of saying the same thing is that no input is used more than once. When you want to try and decide if what you have in front of you is a relation, or more specifically a function, you really focus on what's going on with the inputs. Going back to my first example, which was here, if you look at the relation that I drew and you pay attention to the inputs, so I'll look at my ordered pairs over here, I have a 2, a 3, a 4, and a 4. So the fact that I used the 4 twice is going to tell me that this is a relation, but it is not a function. You can see the input 4 used twice. If you look at the ordered pairs over here, you would notice in the map that I've drawn that the arrow, there are 2 arrows going from the number 4. Here's an example of a function. So we'll look at this in the set of ordered pairs. Let me switch back to black again. If we have the ordered pair 1, 1, 2, 1, 3, 1, and 4, 1. To try and decide if this is a function, we would look at the ordered pairs and focus on the input values. So we're going to pay attention to the 1, the 2, the 3, and the 4. And when you look at this, there are no repeats, so we would say that this is a function. Notice the fact that all of the y values were all the same does not impact whether or not we have a function. It's really all about the x values. Graphically, if you want to know if you have a function or not, we're going to take a look at the vertical line test. So here is a graph of a relation. And here's another one. So from the graphical point of view, a function must pass the vertical line test. I usually abbreviate that simply by VLT. And if you remember from algebra, the vertical line test says that if you take your graph and you draw a vertical line through it, it should pass through the curve once and only once. So this graph over here, which I've drawn, every time I draw a vertical line, notice it crosses the curve once and only once. So this one passes the vertical line test, which means that it is a function. However, if you look at the second figure here, and you draw a vertical line, it's pretty easy to come up with one, where it will cross the curve twice. So this one fails, and it is not a function. This is a second way to figure out whether or not you have a function in front of you, is the vertical line test. The reason the vertical line test works is because when you have ordered pairs on a vertical line, the ordered pairs all start with the same x value. Let's take a look at this second example right here. If you were to put ordered pairs where I have the two x's, you were just to make them up. So I'm going to do that, and I'm going to make up the ordered pair 2, 3 for this first x, and I'm going to say, well, then maybe this is 2, negative 4. Notice that each of the ordered pairs starts with the number 2, and according to our definition of a function, the input value cannot be used twice. So the vertical line is a visual representation of ordered pairs that all start with the same x value. Therefore, you do not have a function when you are talking about a vertical line. Among functions, there are all different kinds of functions that have different sets of restrictions on them. The one that we are interested in this class is the one-to-one function. The one-to-one function is often abbreviated 1-1. So it's a function, which means that the x values are used once and only once, but what makes it one-to-one is the fact that the y values are also used once and only once. So we have a function where each input is used exactly once, and each output is used exactly once. A different way of saying the same thing is that we have no repeats among the inputs and no repeats among the outputs. Remember, I'm using the word inputs and outputs, and I very easily could be using the words domain and range here. So no repeats among the domain values, no repeats among the output values. If you go back to my previous example when we were talking about a function, this one here, where I have the ordered pairs all with 1 in the y value position, we agreed that this was a function, but this is not one-to-one. And the reason it's not one-to-one is because when you look at the y values, every single one of them is the same. So very clearly we have repeats among the y values. Here's an example of a function which is one-to-one. Again, I'm going to use the set of ordered pairs. And if we have the ordered pairs 2, 3, 4, 2, negative 1, 7, and 6, 5. This is a function because when I look across the input values, I see a 2, a 4, a negative 1, and a 6, no repeats, and it is one-to-one. When you look at the output values, 3, 2, 7, 5, none of them are duplicated. From a graphical point of view, you can figure out whether or not you have a one-to-one function. That test is called the horizontal line test. I'm going to get a new screen here so we have some space. So let's draw a couple figures. Here's our parabola again. Here we have two shapes. We're going to use the horizontal line test. So this will help you determine if the function is one-to-one. And it's going to work the same way that the vertical line test works, except you're going to use a horizontal line. So looking at our parabola here, if we draw a horizontal line anywhere through the graph, we can see that it crosses the graph in two places, right here. And that means that this one here is not one-to-one, because it fails the horizontal line test. However, if you go to this figure over here and you draw your horizontal lines, no matter where you draw them, you will notice that the horizontal line crosses the curve once and only once, here and here. So this one passes the horizontal line test. So therefore it is a one-to-one function. Again, why does the horizontal line test work? Let's take a look at some ordered pairs. If we go back over here to the parabola, and you were to make up two ordered pairs that would go where the x's are. So for this ordered pair over here on the left, I'm going to say that this ordered pair is -3, 2. And for the ordered pair over here on the right, I'm going to say that it is 4, 2. And you'll notice that each time I wrote the ordered pair, which lies along this horizontal line, I had to use the same x value. So the same y value. Horizontal lines all have the same y values, so that's why they show a graph that would fail the horizontal line test and therefore not be one-to-one. All right, lastly, let's talk about inverse functions, because this is where we need to focus when we look at the trig. An inverse function will undo the original function. I'm going to go back to that map notation that I used in the beginning of this video. So I'm going to create a new map here. Let's see. Here we go. So in our set of inputs here, we're going to have the ordered pairs, the input values of 1, 2, and 3. So this is our domain. And in our second set over here, our set of outputs, we're going to make 7, 8, and 9. And we're going to call this our range. And remember, we're going to talk about a function. So we're going to map our input values to our output values. This is our function. When we have an inverse function, we reverse this. This would be the equivalent of drawing the arrows in the opposite direction. So if I start at 8 and I go back to 1, if I start at 7 and I go back to 2 and 9 and I go back to 3. The red is the inverse. it brings us back to the beginning. The most important part about an inverse function is what happens to the domain and the range. So right here we can see this. When I started this function, I started on the left over here, and I went from the left to the right. So I went from a set of inputs to a set of outputs. When I reversed it, I started on the right and I went to the left. Where you start are your input values. This is your domain. And where you end is the range. So when you find an inverse, the most important thing that happens is that the domain and the range are switched. When we're working with equations and we're working with graphs, it's easy to say that we switch the x and the y. And this is what happens when you find the inverse of any function, whether it's a trig function, an algebraic function, logarithmic. You will see that we will always switch the domain and the range. Let's take a look at a set of ordered pairs. One 3, 4 6, 2 3, and 5 0. This is a function. No repeats among the input values, 1, 4, 2, and 5. I'm going to call this function f. If we want the inverse of this function, so now we're going to write out the inverse of this function. First of all, the notation for that is going to be f inverse. And f inverse is notated with this little -1 up here that looks like an exponent, but it is read f inverse. Back on my previous slide here, we said we were going to switch the domain and the range, switch the x and the y. That's exactly what we're going to do. We are going to switch x and y. So literally, take your ordered pairs and switch them. 3 1, 6 4, 3 2, and 0 5. Look what happened. I had a function, but my function was not 1 to 1. If I look across this first line up here, I see that the number 3 is used twice in my output values. Then when I switched them, that 3 value all of a sudden became an x value, and now what I have in front of me is no longer a function. So this first one here was a function, but it was not 1 to 1. This right here is not a function any longer. What's most important is that if a function is to have an inverse that is also a function, it must start as 1 to 1. Right, so what did I just say? If a function is to have an inverse that is also a function, it must be, or must start, as a 1 to 1 function. because repeated y values are going to become repeated x values, and we would no longer have a function. Every function, every relation has an inverse. We can always switch the x's and the y's, but we want to make sure that we end up with a function, and to do that we have to start with something which is 1 to 1. To finish this video, let's just take a real quick look as to what this is going to mean as far as the trig is concerned. And I will cover this tomorrow in class. If you take a look at any one of our trig functions, so let's take a real quick look at sine x, and I'm not going to draw it very specifically. Okay, so we've got a sine curve. Looks something like this. Here's our x-axis and our y-axis. It's a function. How do I know that? Because it passes the vertical line test. I can take any vertical line. It will cross my curve once and only once, but it is not 1 to 1. And I know that because it fails the horizontal line test. And if I take any horizontal line, it's pretty easy to come up with one that's going to cross my curve many times. And if you think about all 6 trig functions and how they look, every single one will pass the vertical line test, but every single one is going to fail the horizontal line test, which means that none of them are 1 to 1. So what we have to discuss is how are we going to make these the inverses of our trig functions become functions themselves. The name of the chapter is Inverse Trig Functions. So unless we start with something which is 1 to 1, you're not going to get a function at the end, and we have to figure out how to do that. Tomorrow we will focus on sine and cosine and working with them to make them inverse functions.